All right, well, it's 8 o'clock. Thank you everyone for joining me this evening. So, as I mentioned when I set the event up, this is the first time I'm doing a YouTube live talk. Um, and it's a bit weird, so I don't really know 100% what I'm doing, but I have been assured that people can see my slides, so that's at least good. So, the talk this evening, I thought I'd give a little chat about a sort of an interesting and quirky theory about whether or not dark matter is responsible for killing off the dinosaurs. And also to make the talk a little bit more fun and interactive, I'll also be using Slido, which is this cool app where you can actually ask me questions as we're going along as well. They are moderated, so I won't release them to you all live, just in case some of you ask inappropriate questions, because I know I've invited a lot of my friends to see this talk, and I'm not saying I don't trust you, but sometimes I don't trust you. But if you want to join in and ask questions, essentially you can go to slido.com and you can use the event code #DMDinos. And once you've done that, you should be able to then ask me questions as we're going through the talk. I'll take a look at them and I can release them, and so people can vote on which questions they like best. And at the end of the talk, I can then answer some of those questions for you as well. I'm also going to use this app to do some live polls as well, just to make sure you're paying attention, that kind of thing. So just join at slido.com. And we can have a little bit more fun than just me talking at you for about half an hour. Okay, so I'm now going to go back to the main slides. 1 second. Right, so what I'm going to talk to you about today is whether or not dark matter killed the dinosaurs. And some of you may be wondering whether or not that's a trick question, because as we all learned at school or at some point in our lives, we sort of know what killed the dinosaurs. And what killed the dinosaurs was a giant space rock falling to the earth and obliterating them. So this is a video, not actual footage, because we didn't have TV cameras back then, obviously. But 66 million years ago, a giant piece of rock from space hurtled itself into the earth and wiped out the dinosaurs. And that's something we've all kind of accepted today. It's only relatively recently, though, that people have believed that this was actually what happened to the dinosaurs, though. This idea was first put forward in the 1970s, and people thought it was actually very controversial. So basically, the idea here is that space is very empty, right? If you think about what is around us in the solar system, there's vast amounts of empty space everywhere and very little actual stuff taking up any room. And a good example of this is if you just, take the distance between the Earth and the Moon, for example, you can actually fit all of the planets in the solar system between the Earth and the Moon. So space doesn't have a lot of stuff in it. It's hugely empty. So when people proposed this idea that a space rock flung itself at the Earth and hit us, people thought that was very unlikely, statistically speaking, because if space is so empty, why would a big rock hit the Earth and take out the dinosaurs? So it really wasn't until the 80s and 90s that people started to become more on board with this theory, and in the 90s was really when it started to be accepted. So what we now know, or believe to have happened, is that 66 million years ago, a giant space rock that was at least 10 kilometers across, so therefore, if you stand it on its side, it would be taller than Mount Everest. This piece of space rock hit the Earth and caused an absolute disaster, essentially. So the estimates of how big this rock are range from about 10 kilometers as shown here, but all the way up to as large as 80 kilometers. And this would have had, of course, absolutely disastrous consequences for all of life on Earth and the general sort of health of the Earth as well. So one of the reasons people started to believe that this theory was actually correct is because we found the crater back in the 80s, but in the 90s it was confirmed that the impact crater is actually there from this event. So this is an artist's impression of the Chicxulub crater, and it's about 200 kilometers across. And you can find it in the Yucatan Peninsula in Mexico, right on the edge of the Gulf of Mexico. And it's called the Chicxulub crater because the center is basically located on the town of Chicxulub. So on the left-hand side here, you can just kind of see how big this crater is with respect to the peninsula and the Gulf of Mexico, so really large. And on the right-hand side here, what I'm showing is a map that shows the sort of gravitational distortions in this area. And what that basically means is you can see these concentric circles that are sort of red and yellow. Those are the outlines of sort of the ridges of the crater. So the dashed black line shows you that full 200 kilometer diameter. So it's a really big crater. And that tells us something really big hit us really fast. And when this space rock would have collided with the Earth, it would have set off a whole chain of terrible events that wiped out 75% of all life on Earth. So there would have been a massive explosion to start with that is equivalent to dropping about 20 billion atomic bombs all at once. So that's the kind of bomb that was dropped on Hiroshima in World War II. So 20 billion of those going off all at once in one place. This would have created things like a mega tsunami that would have gone all the way from Yucatan here and brought water as far inland in the United States as Texas and Florida. And it would have triggered a bunch of wildfires. There would have been massive earthquakes and supervolcanoes exploding, all kinds of stuff. And then the sort of end result of this is that you'd have an atmosphere full of ash and dust that would cover the Earth. And the Earth would essentially be thick with this ash and this dust for about at least a few years and maybe as many as 10 years. And that's really devastating for life because no light can get through, so plants can't photosynthesize, the atmosphere becomes slightly toxic, and essentially it wiped out, we think, 75% of all life on the Earth, this single event. So it was very devastating, and that's definitely what actually killed the dinosaurs. They did not survive that. It was pretty bad. And we become interested in this particularly in astronomy because we'd really like to know, there are a bunch of types of space rocks that we're aware of. And the question is, where did this space rock come from and why did it hit the Earth? Is it something that just happened by chance, the dinosaurs were unlucky? Or is there something that happens every now and then that flings giant rocks at the Earth? And if it's the latter, we'd very much like to know that because we have a vested interest in not being squished by space rocks in the future. And if they're going to come, we'd like to know when so we can plan for that and avoid them. But the dinosaurs were not so fortunate. And again, this is an artist's impression of what they would have done when they saw this thing hurtling to the Earth. So what we'd really like to know then is, where did the space rock come from and what would we call it? And in general, we have three sort of general terms for space rocks. We call some of them meteors, we call some of them asteroids, and we call some of them comets. And I think now we're going to do what will be the first live poll of the event. So what we're going to do is just put a poll here, and you can all guess which type of space rock you think killed the dinosaurs. And I'm going to take a look at some of the questions you guys have been sending in. While you vote. No one's voting so far. Oh, here we go. Interesting. So asteroid seems to be quite popular at the moment. And again, if you want to join in the poll and you haven't done, just go to slido.com and use that hashtag DMDinos in the event box to join the poll. I'm just going to leave this running a little bit longer. Very interesting. All right, so overwhelmingly you guys think that it's 45% of you, well almost half, seem to think it's an asteroid. So that seems to be the most popular type of space rock. And this is a bit of a trick question because there's one definitely right answer and then another two answers that are possible. So we know it had to have been a meteor, but we don't know whether the meteor was an asteroid or a comet. So I'm going to talk a little bit about that now. There's some division in the community about which one it would have been. But certainly it has to be a meteor, and I'll explain that when I explain what these three different types of space rock typically are. So I'll just do that now. Good, so meteors, asteroids, and comets. Now, meteor is sort of the most generic, I would say, non-physical description necessarily of a space rock. So we call meteors. That it's basically a term that tells us about how a space rock interacts with us on Earth specifically. So any rock that enters the atmosphere of the Earth gets called a meteor. And we see meteors coming into the Earth's atmosphere all the time, but typically they're very small. So they enter the Earth's atmosphere and they burn up and they leave a little streak across the sky. We often refer to these as shooting stars. But even if a big asteroid or comet came into the Earth's atmosphere, that would also be technically a meteor at that point, because once it enters the Earth's atmosphere, it becomes a meteor. So whatever hit us had to be a meteor by definition. If it hits the ground, it's then a meteorite. So again, it would have become a meteorite when it smashed into the dinosaurs. Now, asteroids and comets then are the two sort of different types of rock that can hit us. And they are different because they come from different parts of the solar system, and therefore they have a different type of composition. So asteroids we find typically mostly in the main asteroid belt, which is located between Mars and Jupiter, which you can sort of see in this middle image here. Now, asteroids are typically very rocky, so they're made of mostly rock. Comets are much further out, so we actually find them way beyond Pluto, much further out from the sun, in this sort of tenuous band out in what we call the Oort cloud. And so the Oort cloud is very far from the sun, and out there, these objects have a very different composition. So instead of being mostly rocky, they're mostly icy. And that's why when comets come into the inner solar system, you often see them leaving behind these beautiful tails as they do so. Those tails form because as the comets come closer to the sun, they heat up and the ice begins to melt. And so that tail is formed from the ice melt from the comets. So asteroid and comets, they come from two different places and they're made of very different stuff. And it matters for our own knowledge about how space rocks generally hit the Earth. We really want to know what type of these things are hitting us and why they get thrown at the Earth at different times. So for the purposes of this talk, we're going to say that it was plausibly a comet. And there was a study in 2013 that argued, based on a study of the Chicxulub crater, that it was very likely to be a comet that hit us. So if you go and study the crater, you can find this element there known as iridium. And the iridium tells us about the amount of debris that was formed when the space rock hit the Earth. So you can figure out how much of the space rock there must have been. So therefore you can work out the size of the object. So that's what gives us this idea that it was about 10 kilometers across. Now, if you take that information about how big the object was and combine that with how large the crater is, you can then get a relative speed that the object must have hit us with. So if we take this size that we think made the crater and the crater size, we find that the object that hit us was moving very, very fast. And this means it's more likely to be a comet. And that's because if you just think about the relative speeds of asteroids and comets, because comets come from further out in the solar system, they tend to be moving with much faster speeds relative to the Earth. So this, combined with the size of the object, means that we think, or at least a group of scientists thinks, it's more likely that we were hit, the dinosaurs were wiped out with a massive comet rather than a massive asteroid. And that's when we begin to need a bit of astronomy, because what we would like to know is why would something that's so far out of the solar system, orbiting way beyond Pluto, suddenly find itself in the inner solar system within striking distance of the Earth? So how do comets make it their way in from the outskirts of the solar system all the way to where the Earth is now? Now, if this is just random and a bit unlucky, if we look and analyse all the craters that we see over the Earth, we would expect that there's no distinct pattern with when they formed. So you can, from dating the craters, you can see when that crater formed, and you would expect to see craters just forming randomly. So we're hit just, unlucky at times. But if there was some kind of pattern, some kind of regularity, then we might have to worry that there is something that happens on a regular basis that ends up throwing comets towards the Earth. And a number of studies do seem to find that there is some regularity with which the Earth gets hit by big comets. So a bunch of scientists have measured this. So they just go, they find massive craters all over the Earth, they date them and figure out when they formed, and then they ask, is there any kind of period here? And what they find is that we seem to get hit by something massive once roughly every 32 million years. Now, if we're getting hit regularly, then it means it needs an astronomical explanation to explain what is causing comets to be ejected from the Oort cloud every 32 million years. And I've put in brackets here, if true, and you should all be kind of looking at me, if you could see me right now, a little bit uncertainly, kind of like this guy. And that's because this is a slightly tenuous basis on which to build the rest of the structure of my talk. Because there is a period that's been measured between the different massive comet impacts on the Earth, but not everyone necessarily believes it. And it's because trying to make that kind of measurement of when comets hit us is quite difficult. There's quite a lot of uncertainty in how often these things can happen. So what I'm showing here is a graph where on the x-axis, so the bottom axis there, we're looking at time, so over the last 250 million years, going back in time. And then on the y-axis, so that vertical axis, we're looking at crater formation rate, which basically tells us how many craters are formed every million years in this case. And so if you look at this, the big peaks are where you're getting a lot of craters. And when scientists analyze this data, they find that you're getting these big peaks roughly every 32 million years, implying that this is a very regular process. But the problem here is that you don't know that you have all the data, right? So what if you missed one comet impact? That would have quite a big impact on the periods that you're measuring. What if a comet hit us but hit the ocean, so we couldn't find the crater? Then we would never know it happened. And what happens if your dates are slightly wrong? Because if you're out by a few million years, you suddenly go from maybe having a regular 32 million year period to a different period or no period whatsoever. So this is basically a way of saying that this data is actually quite noisy. And one thing we know in astronomy is if you try and fit a period to noisy data, even if there's no period there, you can often come away with a quite statistically significant period measurement. So while it seems like there's a period of about 32 million years, not everyone is convinced that that's the case. So, it's a bit of an assumption here. But, the data do indicate that. So it would be interesting to know if that's really true. And if it is really true, then again, we'd like to know why, so we can plan for the next big comet strike. Okay, so let's assume that there is a period. Then we need a triggering mechanism. So what is happening to the Oort cloud every 32 million years that leads to it firing a bunch of comets into the inner solar system? Now, what we think is happening here needs to be astronomical in nature because the Oort cloud is very far from us and it's very far from the sun. So we know that the Earth is about 93 million miles from the sun. And in astronomy, we refer to this Earth-Sun distance as one astronomical unit so that we don't have to measure everything in miles because that's too small for space. Space is too big for miles. So we use one astronomical unit to define this Earth-Sun distance, and then we can define everything else in sort of ratios of Earth-Sun distances. Now, the Oort cloud is about 10,000 AU from us. And what that would mean physically is if I were to take the Earth-Sun distance and shrink it down so that it only occupies 1 pixel on my screen, and then put 5 of my screens side by side, that would then be, 1 pixel would be the Earth-Sun distance, and 5 of my screens would essentially be the distance from the sun all the way to the Oort cloud. So it's much further out than we are from the sun. And what that means is the gravity from the sun that is exerting on the Oort cloud is very, very weak. So there's not a lot holding them in place out there in the very outskirts of the solar system. In general, gravity is the weakest of all the forces, so it's not very strong to begin with. You can sort of defeat gravity every day by picking stuff up. So that's quite impressive. And it drops off quite dramatically the further you get from something. So it's proportional to 1 over the square of the distance, so 1 over the distance times itself. So as you get further and further away, if you move 10 times further away from something, the gravitational pull of that object will be 100 times less. So if you're going to go 10,000 times further away than the Earth, it means that the sun's gravitational force on the Oort cloud is 100 million times weaker than the gravitational pull of the sun on the Earth. And what that means is these comets are in orbits that are really unstable. And so the smallest perturbation could take a comet that's happily orbiting around the sun at 10,000 AU and then suddenly fling it either out into interstellar space, so away from the solar system, or fling it in towards the sun and potentially towards the Earth as well. I do think it's really cool, actually, that we could also eject these comets and send them to other stars. And recently there was an interesting comet found within our solar system that looks like it's an interstellar visitor. So this is just a brief aside, but Oumuamua is a comet that was discovered a few years ago, and it has this sort of long cigar-like shape. A bunch of people thought it might be aliens. It's not aliens, but it is a pretty interesting looking comet. And it's moving at a really fast speed compared to other stuff in the solar system. And that leads scientists to believe that this thing was actually originally in an Oort cloud around a different star. Something came by, ejected it from that cloud of comets, and sent it all the way to visit our solar system. So it's our first interstellar visitor that we've ever discovered. And I think that's really, really neat. But of course, we don't really care about here comets that are being ejected from our solar system because they are definitely not hazardous to us. Maybe to other people, but we should be fine. But if it gets thrown in, then it's going to affect us. So we want to find out what could fling comets out of their orbits into the inner solar system on a regular basis. And astronomers came up with a few ideas, and none of them really work ideally. So I'm just going to take you through some of the ideas we've had in the past. So here I'm showing a picture of our Milky Way. And this yellow star is representing roughly how far we are from the centre of the galaxy. So this is where we currently live. But the sun is also moving around the galaxy. So it sort of goes around the centre of the galaxy with a speed of 220 kilometres per second. And that means once every 240 million years, it goes all the way around our galaxy and comes back to where it starts. Now, as you look at this picture of our galaxy, which is an artist's impression because we can't see our galaxy, you can see that it's not perfectly smooth. You have these beautiful spiral arm features, and there are more stars in the spiral arms than there are outside of the spiral arms. And that as the sun is then moving around, sometimes it will be in the spiral arms, in which case there'll be lots of stars around it, so there'll be a higher density and more gravitational force. And when it's outside of the spiral arms, there'll be fewer stars around it, so a lower density and a lower gravitational force. So one theory was perhaps what's triggering these comets is every time we move through the spiral arms, where there's a higher gravitational pull from other stars, that can kick the comets out of their orbits and fling them into the Earth. Now that turns out that it doesn't work. The density change between in and outer spiral arms and the change in gravity isn't enough to really have that big of an impact on the Oort cloud. And the time period is wrong as well. So we're trying to match a period of 32 million years, but typically we move into a spiral arm once every about 100 million years. So that period is too long and the gravitational force is not enough. So that's unlikely to be what's triggering the comets on this regular period. So another idea was, what if you just have a close flyby with other stars? So we're moving around the galaxy, but so are other stars. And so every now and then we might have a star that, this is not to scale, that might pass somewhat closer to the solar system. And then as it sort of flies by, its gravitational force will be felt by the Oort cloud, and that can give the comet here a little kick and send it flying into the inner solar system. Now, if the star gets close enough, that will completely work. But again, we don't expect this to happen actually on a regular period. In this case, that would be completely random. So it would just happen by chance every now and then, but it certainly wouldn't happen every 32 million years because we have no stars that are doing that at present. So this doesn't work either. The final idea was a bit crazy, and this is the idea that we maybe have a secret second star in the outskirts of a solar system. So the scientists that came up with this called it Nemesis, and it's like the solar system's evil Death Star. So you take essentially what is a brown dwarf star, and that is an object that's somewhere a bit more massive than a planet, but smaller than a star, and so it's not very efficient at burning stuff to be really luminous. So it doesn't radiate in the optical like our beautiful sun does, so it only radiates energy at a lower temperature in the infrared. So we wouldn't be able to see it in the night sky with our eyes. And if you take an object like Nemesis and put it out at 100,000 AU, so 10 times further out again than the Oort cloud, and let it orbit the sun, every 33 million years it would exert a slightly higher gravitational force on the Oort cloud, and that would allow us to sort of rain comets in to the centre of the solar system on a regular basis with the right timescale. Now the problem with this is that it just doesn't work, because while our eyes can't see in the infrared, our telescopes can. And we've done full sky surveys in the infrared. And if there was an object like this hanging out in the outer solar system, we would have found it by now. So this is very unlikely to be the case. So we're out of normal astrophysical explanations, although I would say a Death Star is not particularly normal. But that brings us to maybe some kind of slightly more outside of the box thinking when it comes to trying to explain this periodicity in comets hitting or coming into the central solar system. This theory was come up with by a woman named Lisa Randall, and her idea is that perhaps if we play with the nature of dark matter a little bit, we can get dark matter to influence the Oort cloud and be responsible for flinging comets into the solar system with the right kind of period. So her theory revolves all around this mysterious dark matter that we think makes up most of the matter in the universe. So I'll just show you now the little pie chart of what our universe is made up with, our cosmic inventory. Now, what's always amazing to me is that of all the stuff we can actually see and touch and experience in the universe, like, people, planets, stars, gas, dust, all that ordinary matter, it only accounts for 5% of the total energy budget of the universe. The other 95% of stuff is made up of things that we don't really fully understand. Now, the bulk of that is something that I completely don't understand, which is dark energy. And other than knowing that dark energy appears to be there and is making the universe expand at an accelerating rate, we don't know much about dark energy. And it's also not relevant for comets, so I don't have to explain any more of it to you and show you how ignorant I am when it comes to dark energy. But then the other component that makes up about 25% of the universe and is 5 times more abundant than normal matter is something that we call dark matter. And dark matter behaves just as regular matter does in terms of, it's some sort of matter, it experiences and exerts gravity. However, it won't interact with light at all. So it can't emit light, it doesn't absorb light, it can't radiate, it can't cool. It's just completely dark and invisible to us if we're trying to use our normal telescopes to look at it directly. But because it's way more dominant than ordinary matter, it exerts most of the gravitational force on galaxies in the universe because there's just much more of it. So it turns out to be very important for understanding how galaxies form, why the universe looks the way it does, and things like that. Okay, good. So dark matter is important. But what do we know about dark matter? We don't actually know what it is. We think it's a particle, a relatively massive particle that only interacts gravitationally. So we can't observe it directly. But by studying how stars and galaxies move, we can infer more about it because of the way it's sort of, the gravity is working there. And when we look for it, it appears to be everywhere. So it's been positive for quite a while, so all the way back as early as the 1930s, and even before that, in fact. And Fritz Zwicky was one of the people that was pushing this idea relatively early on. So he was studying a group of galaxies called the Coma Cluster, which I'm showing in this picture here. So you're seeing here a lot of galaxies that are all part of one big group. So they all sort of orbit around each other, they feel each other's gravity, and they're all bound in this big cluster of galaxies. So Fritz was trying to measure how much mass there was in the system. And essentially you have 2 ways of doing that. One, you can just look at how much light is there. You know that light is coming from stars. We know roughly how much stars weigh, so you can just convert that light into a mass and then sum it all up over all these galaxies and you get the mass of the cluster, the total amount of stuff there. Or you can use, gravitational laws and the laws of gravitational attraction to measure it too. So if you can measure how fast all these galaxies are orbiting around each other, you can also infer how much mass, how much stuff there is in this galaxy cluster. And in a universe where you only have ordinary matter, so stuff you can see that's giving off light, those 2 values would be the same. But what Fritz Zwicky found was that when you do this via gravity, you find that there's much more mass, much more stuff there that can be accounted for with just the light coming from the galaxies. So he termed this dark matter, and that's where this name came from. But originally people didn't really buy this concept back then, and that's because his data was a bit noisy. It was just one system, and it was, a very controversial idea that we had this matter that we couldn't see that's making up the bulk of material in the universe. But as more and more people did studies of galaxy clusters and individual galaxies, it became clear that you need something like dark matter to understand all galaxies. And the person who really sort of pushed it forward into being accepted was this woman, Vera Rubin. So Vera Rubin was studying spiral galaxies, like this one in the bottom picture I've shown here. And she was measuring how fast stars move around the disk of the galaxy here. And if you measure that as a function of distance from the center, you can sort of infer how much mass is enclosed within the stars there. So this is a graph on the right here that shows some of her results. So on the bottom axis, the x-axis, we have distance from the center of the galaxy, and on the y-axis, it's the speed of the stars as they're rotating around that spiral galaxy. So you see they all increase, and then we would expect that as you get to where your stars run out, which is sort of roughly aligned with the galaxy below, that this velocity should then decrease again and head towards zero. And that's because you run out of mass, you run out of stuff. But instead what she found was the rotation curves here just flattened out, so they didn't drop off like we would expect. And that tells us that there's lots of mass still being found further out, even though there's no stars. So again, this idea that there's dark matter there that we can't see, we can't detect, but gravity tells us it needs to be there. So it appears to be everywhere, and it's a well-accepted theory now. The only thing left to do is figure out what dark matter is. And ideally we discover the dark matter particle, but as yet we haven't done it. So we're using our observations in astronomy to put constraints on how we think dark matter behaves and what we think it does. So one of the important things then for comets is not just what dark matter is, but where dark matter is found. So in order for it to have a big effect, you'd quite like to have some strong clustering of dark matter near the Oort cloud fairly regularly, so that the gravity that the Oort cloud experiences is higher and can throw comets into the centre. However, for the bulk of dark matter, we think that's not the case at all. Because dark matter can't cool, it can't radiate light, it can't collapse very well. So this picture I've shown here, you've got a galaxy in the centre, and all the normal material there has been able to radiate and cool, and means it kind of spins down into this nice, thin, pristine disk. But dark matter can't do that, so essentially what you find is dark matter is distributed on a much wider scale and in a roughly spherical shape. And that means that the change in density at the solar system is very low, and for flinging comets into the centre, that's actually not useful at all. So if all dark matter is distributed in this way that we measure it to be, then that won't help us with comets. But our assumption that this is the case is based on our model for dark matter, for our model for what the particle is. And we basically always assume that there's only one type of dark matter particle. But in the regular universe, for regular matter, which makes up far less of the universe, we know there's not just one matter particle. Normal matter has lots of particles. You have leptons, you have electrons, you have quarks, you have protons, neutrons, you have neutrinos. There's a whole zoo of particles that we're aware of in the normal matter sector. But in dark matter, we assume that there's just one type of particle. Some of the favourite candidates are things like the WIMP, the axion, and they all sort of have this property where they don't really interact in any way apart from through gravity, and that's why they're distributed in this big sphere. But what if there was more than one type of dark matter particle? And what if some of them were distributed in a different way? So what if we assume that we have some small component, so we know most of the dark matter, based on our astronomical observations, has to be like this WIMP type particle, and it has to be distributed in this big, fluffy, diffuse sphere. But what if we took a tiny fraction of dark matter, say 5%, and made it different? So we could give it properties like it could radiate dark light, which is like light, but for dark matter. So again, we wouldn't be able to see it, but it could be radiating that out. And that would allow it to then not be distributed in a big sphere, but to condense down into a nice thin dark matter disk. And that disk could be maybe very dense. And if that was the case, then that might help us fling comets into the centre. So if we assume we form this nice thin disk of dark matter that looks a lot like the disk of the galaxy, it's sort of in the same plane, but it's made of dark matter, this could actually help us a lot. So one thing we know about the sun as it's moving around the galaxy is it doesn't do so in a perfectly, flat orbit. It kind of bobs around up and down through the spiral arms, just like if you have something sitting on a nice lake like a ball, it kind of bobs around in the water. So the sun does the same thing with the stellar disk. So at times it's slightly higher than the disk, and then gravity will pull it back towards the disk and it'll bob through, and then when it gets too low, it'll get pulled back up again. And the time it takes between passing through the stellar disk is roughly 32 million years, which is the same as our comet impact periods. So if we enhance this disk, so if it's just the stellar disk, the change in density as it bobs through the stellar disk is not high enough for the comets to be flung out of the Oort cloud. But if we added in this thin dark matter disk that's made up of 5% of all dark matter, suddenly the gravitational force can be much more extreme, and that could have a big impact on our comets. So basically you have your sun and your Oort comet cloud looking like this, and as they're going through their little bobbing cycle, they move through the disk. The gravity disturbs these comets on their very fragile orbits, and then can send a bunch of them flying into the inner solar system. And it can do that every 32 million years, just as the data requires. So that is perfect, right? We're all done. Dark matter killed the dinosaurs. It's a cosmic conspiracy, and we should look out for the next time the dark matter disk is going to throw stuff at us, right? Well, let's just say it's not actually a perfect theory. There's still some issues with this, and so I would say probably not. So it's probably not the case, and there's a few reasons for this. For one, to have this very different type of dark matter particle, it would have to form in a radically different way from normal dark matter, which requires sort of a different epoch of formation, and we have no real evidence that that's what's going on in the early universe when particles are being created. So it's not very physically motivated in that sense. So we don't know how they would form or when, and why they would be different to regular dark matter. It's also a little bit inelegant, and we suspect that it wouldn't be a very stable disk. So if you put dark matter into this very thin disk, this very dense disk, it would probably start to fragment and make it a bit clumpy. So it wouldn't be this lovely, perfectly smooth disk that we saw. And again, it just wouldn't really work the way we might expect it to and be stable over millions of years, which of course we would need if we have a regular period. And some of this might be because this is a theory that wasn't developed to actually explain the comets at all, which is one reason why I think it's kind of interesting. So this theory was actually developed to explain a different problem that had to do with how fast the stars in the Milky Way were orbiting around the centre. There was a weird quirk in the data that people didn't understand. And so these authors had argued that perhaps this dark matter disk would create that behaviour. But then as the data improved, we found out that that was just a glitch in the data, and actually you don't need a dark matter disk to explain how the stars are moving in the Milky Way. But then they thought maybe they could apply it to this comet problem because the periods, the timescales work out as being the same. So that is quite interesting. And while it is not likely, it's still not yet been ruled out. And one of the things I also think is quite nice about this theory is that even though it's wacky and it probably won't work, a bunch of future tests can actually tell us, one way or the other, whether this is truly real. One thing we definitely like to do is better measure the crater timeline, so going back and age dating these craters to make sure that we do have a real period there and it's all being done properly. There's also a telescope that's quite famous that we're currently using to map the sky. So the Gaia telescope is a space telescope that's measuring the positions of about 1 billion stars in the Milky Way. And this is going to allow us to put very strong constraints on the density of stuff in the Milky Way disk, whether that's the stars or dark matter or whatever. So it will really be able to tell us whether such a thin dark matter disk that's quite dense can exist at all. So that will be really helpful. And also the particle physicists could do a little bit more work and get their dark matter detection equipment to actually find some dark matter. That would actually be the best way. And they are working very hard on that, but thus far they've not been able to find any dark matter particles. But if they could, and if some of the new sensitive experiments that will come on in the future could do that, that would also actually just tell us what dark matter was, and astronomers could stop coming up with crazy ideas. And some particle physicists quite like this idea. So this was a particle physicist from the US who actually thinks that if you have a chance to kill dinosaurs with dark matter, you should definitely do it. And as he points out, if you look around, we don't see any dinosaurs now. So any model of dark matter that doesn't kill the dinosaurs is therefore experimentally disfavoured. So that's like a particle physicist's view on the matter. So obviously that makes it completely legit, and we should worry about dark matter killing the dinosaurs. Right, so that brings me to the end. So it was a comet that killed the dinosaurs, but we don't know if this is random or a cosmic conspiracy. If it is this thing that happens very regularly, then we don't understand quite why that's happening. Normal astrophysical processes can't explain this claimed periodicity of large comet impacts, but exotic forms of dark matter might. And that brings me to the end of my talk. And so I'm going to now have a look at some of the questions you sent through. And it seems like they didn't get moderated at all, so you've just been able to see all of them. But let's have a look at some of them now. Right. Now, if the same meteor, this is from David the Tall One, I believe he's 6'7". If the same meteor were heading towards the Earth today, how much notice would modern technology give us that it's heading our way? And would we be able to divert it? Well, it's a good question. So potentially you could get a lot of time or not a lot of time, and that's because the amount of space you have to survey to find things like asteroids and comets heading towards us is incredibly vast. And we don't really have enough telescopes working on this to survey all of it. Yeah, we could find out with plenty of time, or we could find out just before it hits. And if we could find it with plenty of time, there are actually a bunch of ideas that people have that could help sort of divert it if you have enough time. Whether it's sending out like things like solar sails, which you could deploy on top of the comet or asteroid that would help sort of catch solar radiation and just shift its course slightly, or other small explosions that could just sort of shift it off its course a little bit. Because you wouldn't need to give it, if you find it early enough, you don't need to give it too big of a push, is my understanding. So you could just give it a small course correction and it would just fly by and avoid the Earth. Why are there two rings in the crater in Mexico? Ooh. I don't really know. So I think it has to do with the way that the impact happens and pushes the Earth out. So you have sort of the initial dent and then a sort of a further dent. And yeah, so that seems to be, so basically what I'm telling you is I don't really know why there are two rings in the crater in Mexico, and that's a really good question. But we see this in a lot of comets, or like a lot of craters, not just this one, but also if you look in some of the really nice ones that we see in the moon as well, a lot of them have kind of like an inner ring and an outer ring. So it's a fairly common feature to see in craters. And I should really know more about that, but I'm too busy studying dark matter, I guess. Okay, so next question. How do you or they begin to date when a rock has hit the Earth? Well, so you can look at the trace elements that have been left over, and essentially you can do things like anything that when you're dating stuff. So carbon dating, using different radioisotopes. So they all have a known half-life. These different kinds of these radioisotopes. So you measure how much is there in different ratios, and that can give you basically a timeline of when they hit the Earth. You can also look at how rock formations have built up since, so you can sort of analyse the rock formations around the crater, and that can give you an idea of when they hit as well. So there's a lot of geology stuff, I think. Again, I'm not an expert on that, but yeah, looking at different isotopes and looking at the rock formation in and around the crater. Okay, so what happened to the ocean life when it hit the Earth? So some of it certainly would have been in very bad shape, because if you don't have any sunlight coming through, then that's going to affect certainly stuff that's dependent on local plant life, for example, in the ocean, right? So if they live near the surface and they require light to grow their food, if they're plant eaters, or they require things that eat plants to then eat, as well, it basically is going to have a huge impact on everything. Now, if you're stuff that's living very, very deep in the ocean, I assume you do a little bit better, because then you don't need as much light. But certainly given that the sun, it had been very little sun getting through for years to a decade, it would have a big impact on ocean life. So 75% of all life was wiped out on Earth at that time. So including in the ocean, they would have seen a big hit as well, I think. Please can you run that by me just again? The whole talk? It's probably taken me a while. So, but yeah, if you have a specific part that I didn't explain very well, please let me know. Is it possible that dark matter doesn't exist at all, but it's just us trying to model our universe using imperfect models that don't work on such large scales? Yeah, it's absolutely possible. Right now, I would say, so there are a bunch of people that are investigating alternatives to dark matter, and they can find some very interesting results. So modified gravity theories are one such attempt here, where we figure that maybe on large scales, gravity behaves differently. So I talked about gravity dropping off as 1 over the square of the distance, but maybe as you move further away, it doesn't have that same relationship. And if we're just assuming that gravity falls off as 1 over the distance squared, then we would, mismeasure how much mass there is on these very large scales. And there are lots of things that modified gravity can do reasonably well. However, they can't explain typically all the data we have coming from things like the cosmic microwave background. They struggle a little bit with galaxy clusters as well. They do a little bit better with disk galaxies. So they're, at best, I would say, incomplete. And they're not able to explain as much of the universe as this idea of dark matter can. So dark matter appears to be a much more successful theory in explaining the vast majority of stuff that we see, so on galaxy scales and larger. But it's certainly imperfect. We always come across small things, often actually on small scales, that dark matter doesn't seem, our idea of what dark matter is doesn't seem to fit well. So I would say at the moment it's our best guess that we have, whatever we are looking at behaves a lot like normal matter, except for it doesn't interact with light. How fast was the meteor traveling when it hit? You said very fast. Yes, so I think it's something like 500 miles an hour is the speed that we think it was traveling at. So very fast. So, so it's much, much faster than you're able to go on any kind of motorway. So I think 500 miles an hour is roughly the figure, the figure I saw. I can't remember off the top of my head, but yes, super fast, much faster than anything normally travels on the Earth. And of course, because it's very massive as well, something that heavy moving that fast has a really big impact. Was the moon ever hit by a comet? Yes, I would imagine probably. So it's certainly been hit by many rocks. So if we look at the moon, just in the night sky, you can see all of these beautiful craters all over the moon. Now, without measuring the properties of these, so measuring sort of the rocks and the composition in the crater of the rocks, it's hard to know whether those are mostly hit by asteroids, which is very likely, or if most of those are coming, or some of them are coming from comets. So I would say it's probably been hit by comets at some point. If we have, it's likely that the moon maybe has too. But probably it's also been hit by a lot of asteroids as well, and that's probably what's made up the bulk of its craters, I would imagine. But yeah, it's possible that it's been hit by a comet, but we'd need to study those impact craters to really know. What is the probability that another large space rock will hit us? Well, I mean, very large on large timescales, right? So if we're talking about getting hit once every 32 million years, on normal human lifetimes, it's very unlikely that any of us are going to experience a really large rock slamming into the Earth. It's just vanishingly small, the probability. But if you're talking tens of millions of years, then the probability that another large space rock will hit us is large. So that just really scales scales with time. So I definitely wouldn't worry about it. For you guys personally, it seems very unlikely that that's going to be a big problem for us. Okay. Given that we are a tiny planet on a spiral arm of the galaxy, how do we know the galaxy is flat and has spiral arms? So we can do that by measuring the density of stars along our line of sight. So if we look through the disk of the galaxy, we can use observations in different wavelengths, so not just visible, but infrared, radio, and we can begin to map out what the spiral arm structure is by looking at how the density of stars changes as a function of distance throughout the disk. But it's actually very hard to do in our own galaxy, you're quite right, because we don't have the benefit of being outside of it. But it has similar properties to other spiral galaxies that we do see, and we can measure at least a couple of the spiral arms reasonably well. So it's sort of looking through the disk in different wavelengths, identifying stars at different distances, and looking how that density is changing as you move away from the sun through the disk of the galaxy. Can we tell if the amount of dark matter is constant? Well, I mean, certainly we don't think any more is being produced at this time, but it's sort of it's not constant in terms of the density. There's the most dark matter in the center of the galaxy, and then it sort of becomes less dense as you go further out. But certainly we don't think it's being produced and disappearing at all times. So the amount that was given to us at the beginning of the universe should be the same as it is now. Did all the dinosaurs die after the explosion? So all the things we think of as classically dinosaurs would have died certainly within months to a year probably after the explosion. So many of them would have died instantly, and they have actually found evidence that a large number of them were very quickly buried by stuff coming from the initial impact. So one of the things that happened when the impact hit was some of the debris in parts of the Earth were flung all the way out of the Earth's atmosphere and then came back to rain down again as sort of like fiery hot rocks much further away from where the initial impact happened. So a lot of them would have died fairly early on, and then more of them would have died over the following year or so as a result of the wildfires, the atmosphere getting burned, the tsunamis, the earthquakes and volcanoes and everything else that would have been triggered. So they wouldn't have all died instantly, but a lot of them would have died straight away, and then they wouldn't have died much longer. Monica, what is the name of the very, very bright star in the sky at the moment? I think, Monica, you might be looking at Venus again, but I can't tell because I can't see out my window. But probably Venus. So a planet, not a star, but it looks like a star. Has any evidence been found that the meteor crash site that proves this? How does a 10-kilometer rock disappear? Well, essentially, again, it's because it's hit the Earth so fast, and it really would have just obliterated itself, especially if it's a comet. It's made of it's like a dirty snowball, so it's a lot of ice. And with an explosion that's equivalent to 20 billion atomic bombs, that can really vaporize any kind of rock that hits. So that's what's making it disappear. It's just getting burnt up by the explosion when it hits the Earth. Have clicked option but not showing. So that must be someone who was trying to guess what space rocket was. That's Alan. He's got it now. Why is the sun moving around the galaxy independent of the spiral arms? Well, the spiral arms themselves are kind of like density waves, so they're moving as well, but they move differently because they're sort of winding with time or changing with time. So yeah, they move in different ways. Was it Planet 9? Oh, Planet 9. So probably Planet 9, we still don't know exactly where that is, or even if it's definitely real. So I guess I'd have to look into the Planet 9 stuff more, but depending on exactly where it was and how massive it was and how frequently it's orbiting around the sun, it potentially could. But again, I suspect unless it's at the perfect the perfect distance from the sun, it won't give the period that the comet people want. But if it was at the exact right place with the exact right mass, then yes, just kind of like the sort of killer star, it could also be that. And how are we sure that Chicxulub was the one that killed the dinosaurs? It's just from dating the crater, really. So we know that big impact happened, and then we can also find dinosaurs buried in sort of the debris that came from that as well. So all of that comes together to sort of show us that Chicxulub was in fact the one that killed the dinosaurs. So that we're very confident based on the age and how the debris spread and where we find the dinosaur bones that were killed by the initial blast and the initial comet hit. So for those reasons, we're very sure that that is the one for sure that killed the dinosaurs. All right, good. So I think that's all the questions now. And so I guess just to end the talk now, it's almost perfectly on time as well. Oh, how long did it take the meteor to travel from its origin to the Earth? Oh, a long time. I can't do that maths in my head, but if it's travelling at sort of a few hundred miles an hour or so relative to the Earth, and it's coming from 10,000 AU, it's going to take a while to get all the way from the outer solar system. And that's a really great top question, Thomas. But yeah, off the top of my head, I'm not sure, so I'll have to look into that. But yes, thank you for that question. Very good. All right, so that's all of your questions. And then I just had one last question for those of you that are still there. In case I were to do this again, do you guys have a preference of what I would talk about? So I've given some options here. So we could do galactic archaeology, which is what I do my research on. The first image that was ever taken of a black hole. Is Pluto a planet? Just dark matter more generally. Or maybe you have something else that you would like and you can write in the comments in the question part. So yeah, I'll let you vote on that. And otherwise, thank you very much. Galactic archaeology is very popular with one person. But yeah, other than that, I think that's everything I wanted to chat to you guys about. So thanks a lot for coming along and for asking loads of great questions. Actually, that was really fun. And it gives me confidence that the talk actually worked, because I'm just looking at my computer screen. So it's really, really hard to know what's happening. Wow, so far galactic archaeology is very popular amongst all of you. Oh, we're getting some votes for other things now as well. All right, so I'm going to leave this running for just a couple of minutes. Um, but yeah, I think just thank you all for coming along, and I'll come and do this again sometimes, possibly on galactic archaeology based on the current poll results. So thank you everyone for coming. All right, so it's very clear there's a winner here, I think. So my next talk that I'll arrange to give in the future will be on galactic archaeology, and we can talk about how I'm basically like a female Indiana Jones, but better and cooler. Awesome.